Welcome to the presentation on fundamental frequency model for post-filtering at low bit rates in a transform domain speech and audio codec. My name is Neha Das and I'm a doctoral candidate at Aalto University, Finland. This work was performed in collaboration with Professor Tom Bäckström from Aalto University, Finland and Dr. Guillaume Fuchs from Fraunhofer IAS, Germany. Speech coding is an important component in all systems that deals with the transmission and storage of speech. Therefore, it optimizes resource consumption for transmission of speech while at the same time maintaining and providing highest speech quality. Post filters are a method used to improve signal quality at the decoder. However, conventional post filters sometimes require processing at both the encoder and decoder, often require the transmission of additional bits, and are highly dependent on other functional blocks of the codec for optimized performance. An alternate approach for post filtering is to include source models at the decoder. In our previous work, we proposed methods that incorporated spectral envelope models at the decoder. While these methods showed higher output gain, we also found that incorporating models for fundamental frequency in the post filters could also help additionally to improve the output quality. Therefore, in this work, we propose low complexity post filter at the decoder, which includes and incorporates speech fundamental frequency models. So going through the signal model of our methods, very simply put, speech can be modeled as or said to be produced by glottal excitation that is filtered by vocal tract response. Therefore, filtering in the linear domain can be seen as a multiplicative operation, which in the log domain would become an additive operation. So we can write the log magnitude of speech as the summation of the excitation and the spectral envelope model in the log domain. So in this work, we propose to model the decoded signal, precisely speaking the log magnitude of the decoded signal as a sum of the harmonic model and the spectral envelope. Also, we would need to address the noise component in the decoded signal, which is comprised in the term x of x underscore n. Our goal through this work is to find an optimal filter A, which is also linear filter but incorporates components such as a spectral envelope model and the harmonic model in its features. The optimization criteria that we have followed is the minimizing the mean square error, which finally yields the Moore-Penrose pseudo-inverse equation, which provides the optimal filter A. Note that capital D is a feature matrix. The system overview is shown here, which can be divided into three parts: the feature vector extraction part, the offline training, and the runtime post-filtering itself. The features used again are the spectral envelope, the fundamental frequency model, and the magnitude spectrum, which addresses the noise component of the decoded signal. All of the features are extracted in the log domain. The fundamental frequency F0 model is obtained by extracting the largest sepstral coefficient I and two adjacent coefficients from the sepstral domain and inverse FFTing it to get a feature vector that is of the size of the magnitude spectrum itself. We do the training, modeling, and the study both in the frequency domain and the perceptual domain. And finally, the features during the runtime and also during the training is computed from the decoded signal. On studying the computational complexity, we find that matrix multiplication with the filter comprises of the highest complexity. However, on looking at the singular values of the filter, we find that 95% of the information is comprised or held in 25% of the coefficients. Therefore, through dimensionality reduction methods, we can easily reduce the complexity by 75%. So we use the timid data set for the training and testing. Due to the inherent proportion of the male and female samples in the dataset itself, 1,000 speech samples comprised of 340 female samples and the remaining were male samples. The samples were randomly chosen from the training set of TIMID. We used a codec similar to the EVS codec in the TCX mode to obtain the decoded signals. And the proposed post filter was applied on top of the LTP post filter. The spectrograms here show the clean signal, the decoded signal with the LTP post filter, and an enhanced signal which uses the proposed post filter. If we observe, we can see that the decoded signal with the LTP post filter has a lot of discontinuity over temporal frames. These discontinuities render perceptually as musical noise. While on the other hand, in comparison, in the enhanced signal, we see that these temporal discontinuities are to a great extent reduced, and also the quality achieved in terms of the output gain is specifically due to this feature. So for the objective evaluation, we tested the post filter on 118 test samples, which comprised of 40 female samples. And these samples were randomly selected from the test set of the timid data set. The objective measures used were the absolute and differential perceptual SNR, which is basically the signal to noise ratio in the perceptual domain, the PES scores, and the Polka scores. So looking at the PSNR, we can see that on an average there is an improvement of 1 dB with respect to the decoded signal for both male and female samples. However, the variability in the PSNR is much higher compared to the female samples. In terms of the PES score, we see that while for females, on an average, we observe improvement of 0.2 MOS for both frequency domain and perceptual domain modeling. We do not see any improvement as such for the male samples. However, in terms of the Polka scores, we see an average improvement of 0.5 MOS for females and 0.25 for males. So from the objective scores, we can see there is a consistent improvement for females in both the frequency domain and the perceptual domain modeling. However, for males, depending on the objective measure, there is a difference in the improvement. We also conducted subjective evaluation using the MUSHRA listening test with 10 listeners. The test comprised of 12 test items, out of which 6 were female and the remaining were male. Each item comprised of 6 conditions. The standard conditions of lower anchor, which is the low pass speech sample at 3.5 kHz, the hidden reference, and the decoded speech, LTP post-filtered speech, post-filtering in frequency domain, and post-filtering in perceptual domain. To select the samples, 4 samples were randomly chosen. 4 other samples were chosen which showed the highest Polka scores, and 4 samples were chosen which showed the least Polka scores. We observed that for both the perceptual domain and the frequency domain modeling, the proposed post filter shows a gain over the decoded signal. However, the post filter modeled in the perceptual domain showed a much higher improvement in MUSHRA scores with respect to the LTP post filter decoded signal. So all in all, we can say that while the objective scores did show an improvement both in the perceptual domain and the frequency domain, It's mostly the perceptual domain post-filter that is shown to have a perceptual influence over the LTP post-filter. So in conclusion, speech coding is required for the efficient transmission and storage of speech while maintaining quality of speech. In this work, we propose a post filter for enhancement in speech and audio coding, which incorporates information on harmonic structure of speech. Our objective measures through PSNR, PESC, and Polka scores shows positive improvement over the decoded signal and the LTP over the LTP post-filter decoded signal. We observed that the MUSH objective scores were much higher for the females in contrast to the males. This can be assigned to the higher accuracy in obtaining the fundamental frequency model for for female samples. While in both the domains the MUSHRA points were higher, we observed that for perceptual domain modeling, there was a gain of 7 MUSHRA points with respect to the LTP post-filtered signal. Listening tests also showed that the post filter is successful in removing artifacts that are caused due to temporal discontinuities. With this, I'd like to end my talk. I'll be happy to address your queries now.